guys, lesson 7.1, task 1. All right, today we're going to look at inverse functions and function composition. So inverse functions is a big part of our standardized test or our EOC. Function compositions I've never seen on the EOC, but individually I have seen this a lot on the ACT. So we're going to look at how compositions can be used to check to see if two functions are inverses. All right, composition or compose functions. You learn how to combine two functions to create a new function using arithmetic operations. A composition of two functions is another way of combining two functions to create a new function. Connect to vocabulary. One of the meanings of the word compose is to be formed from various things. The composition of two functions is an operation that combines two functions by using the output of one function as the input of another function. To see how composition works, consider a bicycle with gears. The front gears, to which the bike's pedals are attached, have teeth, as do the rear gears on the bike's rear wheel. A gear ratio is the ratio of the number of teeth on one of the front gears to the number of teeth on one of the rear gears. The gear ratio tells how many times the rear wheel will turn for one revolution of the pedals. All right, so you can see here is the rear gears, okay, and you've got the front gears here. All right, it says suppose the gear ratio for a particular pairing of front and rear gears is 2:1. If P is the number of pedal revolutions and W is the number of rear wheel revolutions, then W is a function of P, where W equals 2 times P, and that's because the ratio is 2:1. So W equals 2P. So the rear wheel revolutions, D equals 26 pi W. All right, if a bike's wheels are 26 inches in diameter, then the circumference of each wheel is 26 pi inches. The distance in inches the bike travels is a function of W, the number of rear wheel revolutions. D equals 26 pi W. All right, using the information given, write the distance D as a function of the number of pedal revolutions, P. Enter the coefficient in the first box and the variable in the second box. All right, so if we look at this example, all right, so if we look above, okay, remember that it says that W equals twice P, okay? So we're going to use that and plug in twice P. So if you say D equals 26 pi W, but now we're looking for D of P, we're going to have 26 pi, and instead of W, we're going to have 2P, because W equals 2P. So D of P equals 26 times 2 is 52 pi times P. So for the boxes down here, where it says enter the coefficient in the first box, the coefficient would be 52 pi times, and the variable goes in the second box. We're using P now instead of W because we replaced W with 2P. All right, I just explained the reasoning, so we're going to move on to letter B. A composition of functions f of x and g of x is denoted by f of g of x equals f of g of x. So this is notation that you need to be familiar with. This is the notation you will see when you take the ACT and you see a problem like this. In the diagram, notice that g of x is substituted for x in f of x. One requirement for the domain of a composition function f of g is that x be an element of the domain of g. What other requirements must be imposed on the domain of f of g for the composition function to be defined? Now, be aware that this is not a dot, like a multiplication symbol. This is like a little circle. So it's f of g, where if you see f times g, it would just be a dot. F times g is that. This is a composition of functions, f of g, okay? And that's just how you read that. All right, so composition of functions. Let's see how to fill in the blanks here. The function, okay, so we've got an input x, the domain is of g, and the output is g of x. So it's just like x and f of x. This time we're having x and g of x. So our range here of g. And then we're going to take whatever the output is here, and we're going to input that back in to the function or the domain of f. And then that turns into an output, or the range is your output of f. So f of g of x is going through this process. So the function of g of x is an element of the domain of f. All right, given the functions f of x equals x squared and g of x equals 2x, what is the value of f of g of -2? All right, so algebraically to solve this, what you do is you always start with the first function. So -2 gets inputted, or you input -2 into g function. All right, so we're going to have 2 times -2, and that equals -4. All right, so that is your output for g of x. That's your g of x. So we're going to take the output, and then we're going to plug it into the next function. So the output now goes into f of x. So what does it tell us to do? F of x tells us to square it. So you've got -4 squared. -4 squared is 16. So f of g of -2 is just 16. All right, so let me write that a little cleaner here. So g of x is 2x. So I'm going to substitute my -2 in here. That becomes -4. So I'm going to take -4 and plug that into my f of x function. So I've got f of x equals x squared. So I'm going to take f of x, and I'm going to substitute my -4, or my output, and that's going to give me -4 squared, or 16. So it's just kind of showing you the process that you go through there. All right, given the function f of x equals x squared and g of x equals 2x, what is the rule for f of g of x? What is the domain of the composition function? All right, the domain, the rule for f of g of x is, so we take this and we square it. So they're trying to like say, what is the rule combined? So you do this first, and whatever that is, we're going to put it here and square it. So that's going to be 4x squared. All right, so the domain of the composition of functions is, should be all real numbers. All right, that's all for task 1. If you have any questions. All right, continuing with lesson 7.1, this is task 2, inverse functions and function composition. Find inverse functions. An inverse function denoted as f inverse of x, and this is a symbol that you definitely need to know throughout this class. F inverse of x is the function that undergoes the operation of a function f of x. This means that f of x of f inverse of x of f of x equals x. So this is just what we were talking about a minute ago, a composition of a function where you plug one output in and it becomes the input of the next function. So it's going to say if you put one, if these are inverses and you put one into the other, you're going to get what you started with for all values of the domain for f of x. So that's how you can check to know if it's an inverse function. And we'll look at that a little bit more detail. The diagram shows the mapping from the domain to the range of the function f of x, and then also for its inverse, f inverse of x. This shows that f inverse of x undergoes the work of f of x, returning the original domain values. All right, so if you have f of x, and this is your domain and this is your range, the inverse of this function would be just the opposite. So the range becomes the domain, and the domain becomes the range. You can see that these are just switched. -2, -10 becomes -10, -2. So if you have an ordered pair, okay, so if you have an ordered pair, and the ordered pair is -2, -10, and it asks for the inverse, all right, the inverse would be -10, -2. All right, so this point is the inverse of this point. All right. You can use algebra to determine the inverse of a given function. Having determined the inverse function, you can verify that the two functions are inverses by using composition to show that f inverse of f of x equals x, and vice versa. Determine the inverse function of g of x equals g of x equals 2x plus 4. All right, so I'm going to show you the way we always do inverses is just by switching the x and y. So we're going to have y equals 2x plus 4. The first thing you're going to do is switch x and y. Everything else stays the same. Just switch your x and y and then solve for y. Okay, so you subtract 4. X minus 4 equals 2y. And divide by 2. Divide everything by 2. So y equals 1/2 x. Just assume that to be a 1 there. So 1/2 x. And then -4 divided by 2 is -2. So the inverse of this function would be this function here. All right, so they left it g inverse of x, they left it at this step right here. So I just reduced it a step further, but you can leave it here or go ahead and reduce it here. And I'll tell you, on the EOC, you may see it both ways. Sometimes it's like this, and sometimes it's like this. All right. How does the order of operations when evaluating g of x for a given value x compare to the order of operations when evaluating g inverse of x for a value of x? All right, so the order of operations of g of x, what does g of x tell us to do? It tells us to multiply x by 2 and then add 4. So we're going to multiply by 2, followed by adding 4. G inverse, so if you come down here and say g inverse tells us to take x and subtract 4 and then divide by 2. Tells us to subtract 4 and then divide by 2. So that's just like if you have this function, what do you do? Okay, so multiply by 2, add 4, subtract 4, divide by 2. Those are opposite operations, and you can see why those are inverses. All right, use composition to verify that g of x and g inverse are inverses. All right, so if you want to verify this, you just choose a number. Let's choose something like 1. So if we have y equals 2 times 1 plus 4, we get 2 plus 4, which is 6. So we take 6, we plug it into the inverse function. So what is 6 minus 4 divided by 2? 6 minus 4 is 2. 2 divided by 2 is 1. Okay, so I started with 1 as my x. I plugged it into g of x. Then I took the output and plugged it into g inverse of x, and I got back to where I started with. So that proves that those two functions are inverses. All right, relationship between inverse functions can be visualized by graphing both functions on the same coordinate grid. Use the graph of g inverse of x to find g inverse of 0 and g inverse of 4.